Okay, guys, you probably figured this out already, but if you didn't, that's fair too. So if you've got an original function, you want to find the rate of change of that function, you can just use this magical power rule, which you'll spend months figuring out how to derive with limits and all that fun. But really, like in practice, all you got to do for polynomials is you take your coefficient. By the way, the number just multiplying the variable to whatever power is the coefficient, and then what power the variable is put to is the exponent. So your coefficient for the derivative is just your original function's exponent times the original function's coefficient. So we got 3 times 2, 3 times 2. That gives us 6. That's our new coefficient for our derivative. And our new exponent for the derivative is just whatever it was originally, minus 1. And it's always minus 1. So just 2 minus 1. If this was to the power of 3, it would be 3 minus 1. So it would be 2. Notice usually you don't write something as to the first power. You just leave it absent. But I wanted to show that it was 1 less. And do something you're likely to run into. All right, last thing I want to go over is, hey, what if you got this big complicated one? It's actually not that hard. You just do the same thing, one little piece at a time. So if the derivative of 6t to the third power, to find the new coefficient of that, we will just take the 6, multiply it by the 3, we'll get 18 for the new coefficient for the derivative, and then the power is just 1 less than it was before, so that would be t squared. And then we just keep adding them together. We find the derivative of this guy, so our new coefficient would be 3 times 2, old coefficient times old exponent. 3 times 2 is 6. T, and then our exponent of the derivative is just 1 less than the exponent of the original, t to the 1. I'm going to leave it out. Normally you'd write a 1 there. And then this is secretly t to the 1. If you just see a t there, it's t to the 1. So your coefficient, it's basically 2 times 1 to find the new coefficient. But then 1 minus 1 is 0, and anything to the 0th power is just 1. So you can think of this as 2 t to the 0, but t to the 0 is just 1, so it's just 2. So anytime you've got something that's just multiplying t or x or whatever you're taking the derivative with respect to, just basically get rid of your variable, and you're left with just the coefficient. And for the next guy, this is secretly being multiplied by 1, which is just t to the 0, right? So what's our coefficient going to be? It'd be 1,237 times 0 to find our new coefficient. So this isn't a factor. And that makes sense because if you think about it, if we've got some original function that's like this or whatever, we can't tell, like, our derivative is our rate of change, so it tells us our slope at any given point. So we know our slope's 0 here, we know our slope's there, but we don't know how much the graph is shifted up or down, which is determined by this guy. So this guy here would have exactly the same, assuming I drew it the same, it would have exactly the same derivative because it's just shifted up or down. It's just got different by this. So since this is just a function that represents the slope at any given point, and how shifted up or down your graph is does not affect the slope at all. Any terms that shift the thing up or down, any constant terms, go away. So that's a loss of information. So you need more information to go backwards, which we'll get into when we talk about integrals. Anyway, thanks for listening.